We continue looking at regulatory frameworks and compliances, specifically promoting regulatory clarity and consistency. Regulatory clarity fosters investors' confidence and encourages market expansion. Policymakers should work to harmonize or find mutual recognitions of regulations over Europe, reducing discrepancies that can hinder the deployment of systems. Transparent permitting processes with simplification, standardized application procedures to fasten the process, and clear compliance requirements with traffic light systems will facilitate the efficient adoption of groundwater heat pump systems while minimizing administrative barriers. A robust regulatory framework also includes monitoring and enforcement mechanisms. Ensuring that regulations are consistently applied and enforced helped to maintain public confidence, but also to protect natural resources and to support the long-term viability of groundwater heat pump systems. Looking at sustainability monitoring and risk management. Regulators should ensure that there is efficient monitoring and effective risk management of the implementation of groundwater heat pump systems. There are three key elements to optimize system performance: minimizing environmental impact and mitigating technical, regulatory, and economic risk, which are described in the following. Sustainability in groundwater heat pump systems. To ensure sustainability, the design must be based on detailed hydrogeological studies. This allows us to prevent negative impacts on underground ecosystems and to avoid thermal interference between nearby installations. In addition, the energy efficiency of the system can be optimized using advanced heat exchangers and the reduction of thermal losses. Integration with renewable energy sources is also key, allowing for a reduction in the use of fossil fuels and lowering CO2 emissions. Second is the monitoring strategies for groundwater heat pump systems. Monitoring is a tool to evaluate the performance of groundwater heat pump systems and to ensure their efficiency and safety. Among the main parameters to be monitored are groundwater temperature before and after heat exchange, extraction and reinjection flow rates, the soil thermal conductivity, and water quality. In addition, it is important to monitor the energy consumption of the system to identify opportunities to improve operational efficiency. To carry out this monitoring, several technologies could be employed, such as temperature and flow sensors installed in the extraction and reinjection wells, automated water quality analysis systems, and digital platforms for data management. In recent years, the use of artificial intelligence and machine learning has made it possible to predict systems failure and optimize performance by analyzing operating patterns. Continuous monitoring not only makes it possible to detect problems before they lead to critical failures, but also helps to optimize systems efficiency through real-time operational adjustments. Lastly, there's the risk management in groundwater heat pump systems. Risk assessment methodologies facilitate the identification of potential environmental and operational threats. Adaptive management strategies allow regulators to adjust policies based on monitoring data and emerging challenges. Risk management in groundwater heat pump systems should follow a holistic approach that combines early threat detection, implementation of monitoring and predictive maintenance plans, the development of fast response strategies to failures. In addition, financial aspects of the project must be considered and operational costs planned to ensure a long-term economic viability of the project. Moving on to the encouragement of the adoption of groundwater heat pump systems. Policymakers can facilitate the adoption of groundwater heat pump systems. This requires a comprehensive approach that combines economic incentives, favorable regulatory frameworks, education, and market development, along with their integration into urban and energy planning. Reducing upfront costs with subsidies and affordable financing can facilitate their adoption by a wider public. Clear regulation and simplified administrative procedures can also reduce barriers to installation and operation. The table shows, for instance, regulatory frameworks and supporting policies. A clear and simplified regulatory framework encourages the adoption of groundwater heat pumps. Standardization of processes and inclusion of the system into sustainable building codes can facilitate the integration. It is also important to establish environmental regulations that ensure responsible use of groundwater without discouraging innovation. Faster permitting also has to be set up. Second, there is awareness, education, and market development, as a lack of knowledge about groundwater heat pump systems limits their adoption. Information campaigns and technical training for professionals and authorities are needed. Innovative business models such as energy leasing can facilitate access. Success stories and demonstration projects can increase confidence in technologies. We are also talking about integration into urban and energy planning. For large-scale adoption, groundwater heat pump systems should be included in decarbonization strategies and district heating networks. Land use planning should identify optimal zones and avoid land use conflicts. Collaboration between academia, government, and industry is needed to drive innovation and competitiveness.